So I'm really excited to present Alex Gaeta from the university. So Alex is the David Reiki Professor of Applied Physics and Material Science at Columbia University. Was that correct?
That's good. That's
yeah. So he did his PhD in optics from University of Rochester, and he has many hundreds of publications, patents. In terms of scientific contributions, Alex has made a lot of groundbreaking advances on photonics, nonlinear wave propagation, and all sorts of optical media. Most recently, a lot of really fundamental work in chip-scale devices. That's exciting that we're going to hear about today. And so, also he's won many awards, including the Carl H. Pound Award years ago. Let's give him a warm.
Thanks. Yeah, let me thank Amir and Marty and Juna for the invitation to come here. I was, of course, coming to Stanford, it's always amazing scientifically for me. I always learn an incredible amount. But as I was telling Ben and Shanhui this morning, this is actually probably the place that I have, outside of Columbia, the most friends as well. So it's an indication of a great culture that's been established here. So I'm going to talk today about quantum photonics and the frequency domain, not so much maybe about the integrated photonics that you mentioned, but and maybe some of this will seem like this is obvious, but at least for me, when I first started looking at this about 10 years ago, there were a lot of interesting ideas that were not so obvious to me. Certainly, it's an area that's close to Shanhui's work that he's been pioneering for the last decade or so. So at the heart of everything I'm doing, and actually I thought when I was going to come here, I was going to focus on quantum frequency conversion. But for the most part, this is kind of more of a tool for what I'll be talking about today, and less on the actual physics of quantum frequency converters. But it's a very simple idea: is that you have some state of light, quantum state of light, that you can convert into a different color. It's kind of a very almost trivial idea. But it's not so easy to do because there's a lot of issues in terms of doing this in a way where you preserve the fidelity of the field, that you can do it really efficiently, and so on. And certainly, as I at least put it here, I haven't even said that this is necessarily optical or that's optical. It can be the microwave domain. We have David and Jonathan here who are kind of leaders in the world on doing this with superconducting qubits. It's doing what's called transduction, which is really a form of quantum frequency conversion, but it's doing it from microwave to optical. Actually, if you look way back at Bob Boyd's thesis under Charles Townes, his thesis actually was converting mid-infrared photons to optical photons for astronomical applications. So back then, it's kind of a long-standing problem. Of course, now we have detectors that work really good in the infrared, so that's become less important. But I'll focus on this part here, which is really developing heterogeneous quantum networks. And I would say it's kind of something that no one's really talking about, but I would say is absolutely critical. And so I took this picture from the web, and this is all, I think it was a paper that was focusing on quantum network. I think this term was first coined by Jeff Kimball, roughly about 25 years ago. But it shows all these different kinds of devices, quantum computers, you have, of course, on satellites, you have all these quantum communication parts, and there's a lot of quantum devices out there. What you don't see is how this is going to work. And in electronics, in classical communications, a bit is a bit is a bit. It's really easy to convert an electrical bit, which is just, you turn out, you give a little electrical pulse, and you use that to drive a laser or a modulator. It's really easy to create a photonic bit. But in the quantum domain, it's not so easy to do that. And it's really, what's missing in all this is actually the interface between how you're going to connect all these different quantum systems that are probably all operating at different, why don't we say, different parts of the electromagnetic spectrum. And so if you're going to really realize a quantum network, we have a lot of work to do on developing quantum frequency conversion. That's just my overall statement. So certainly this is an important part. I'm just showing here, and this is not even a complete list, but it just shows you, for example, if you want to connect quantum memories across, let's say, any kind of distance where you need to transmit on an optical fiber. So you have the optical fiber in all the different bands, and of course we use that because they're low loss there. And of course you can go maybe 30 kilometers before you need a quantum repeater, and that's a whole nother issue. Well, you need quantum memories for that as well. But we have a whole bunch of different devices from strontium all the way up to diamond NV centers that perhaps you want them to talk to each other. And of course, even within this little group here, you have to do quantum frequency conversion. And of course, if we do want to connect them far apart, then we have to go out to this wavelength and then come back and so on. So there's a lot of challenges here. I'd say we barely even scratched the surface. And of course, there's a lot of work that has gone on here at Stanford. There's, of course, a number of groups that are working on this here. So the key requirements, and it's pretty simple. You actually have to, and this is the one that's usually the killer, is you have to do this at roughly unit efficiency. If you do it anything below a unit efficiency, that is introducing loss. So it's equivalent of adding loss to the system. And of course, you don't want any added noise. Again, sounds trivial, but doing this process and achieving these is challenging. So that's just selling you quantum frequency conversion. And that's to do perfect quantum frequency conversion, 100%. Okay. What I want to talk, and most of my talk will deal with, is actually quantum frequency converters also allow you to do something that's quite a bit different, which is to introduce a new dimension in which you can do quantum photonics or quantum optics or quantum information processing, and that's to utilize the frequency domain. So this is probably the simplest way I can think of in optics to generate an entangled state. You take your single photon, you have a 50-50 beam splitter here. The photon can go here, it can go here. You can write the output state as 1001 state. Pretty simple, straightforward. And in fact, if you look, so this is just taken from Psi Quantum. They actually showed like one of these pictures here. This is back when they were working with silicon. They've now since moved to silicon nitride. And whatever your opinion of Psi Quantum, I'm just showing the picture. But it's illustrative is there's a number of interesting parts here. They have a pump field that comes in, generates correlated photon pairs. You then have to do all the filtering here. But I'm just going to focus on this last part here, which is all these different beam splitters. These are what's doing all the entanglement here. We can argue that there's a lot of problems here. There's a lot of problems here as well. And one of the real problems is it's the scaling in terms of losses, which is they actually just spoke. They were part of a symposium. They came to Columbia. There was this year is the International Year of Quantum. Didn't know that from UNESCO. And it turns out that I asked them, so how many of these devices do you need for generating the photon pairs? And they said 10 million. And I said, how many wafers is that? Because if you're doing 10,000 silicon nitride wafers. So that is just this part here. And this is going to be even bigger. So we're talking scaling in terms of losses. This is going across, buildings in terms of size. And of course, the losses, as good as silicon nitride is, it's not going to get you there. So there's lots of issues with loss, even with this system. So what I'll tell you about, and is really the heart of the talk, is imagine that we have some device here which takes my photon color blue and converts it with 50% probability to green. Okay, so this is like a quantum frequency converter. If it was 100%, it would take my blue photon and convert it to green. But if I keep it at 50%, now if I look at the state at the output, it looks just like my beam splitter. But now it's a beam splitter in the frequency domain. And so this type of entanglement can be done in the frequency domain. And the nice thing about it is, perhaps I can scale this up in the frequency domain, because that's as Hong-Ou has used the term, synthetic frequency. And it doesn't require really to make my system bigger. Sure, in the frequency domain, but it doesn't require a bigger spatial dimension. And that to provide some advantages, or at least another degree of freedom that allows you to overcome loss. So I'm going to call this kind of my frequency beam splitter. I'll tell you how we do this, but this is all just done with doing the frequency conversion process, but not necessarily going up to unity efficiency, but keeping it at, let's say, 50%. But of course, if you have a really good frequency converter, it's really essentially like, you have a two-state system here, and I can put my system anywhere on the Bloch sphere. And as we see, these frequency converters can in fact do that. So as I mentioned, the frequency domain has been used in classical communications a lot. It's the heart of wavelength division multiplexing. It's very powerful because, again, the fact is, at least in the as long as you don't include nonlinearities, each of these can operate separately and they don't overlap each other. In the quantum domain, we actually want the coupling. That's the key part here. And we have to introduce some type of unitary coupling that allows us to bring these frequencies together and couple them together. And again, the powerful part here is that the losses don't scale with size. So we can keep adding frequencies here. Ideally, you could do this all in one waveguide. You're not increasing the losses. That could be a big advantage. And of course, the key requirement for all this is that the coupling between them should be reconfigurable. And again, quantum frequency converters that have been developed in nonlinear photonics allow you to do that. So I'm going to show two versions here. And again, at Stanford, normally I'd never show the Chi-2 version, but I'll show the Chi-2 version. And so this is, what the converter looks like. I'm not going to go through all the math, the details, but it's just to give you some idea that you have some second order nonlinear medium, you have a signal here, and you have this photonic process in which this blue photon can get converted to this red photon, and it's mediated through this pump. And it turns out, if you just go through all the math in terms of the idler and the signal in the quantum domain, it obeys this following equation. And this is different from the usual parametric processes where, for the most part, we're always focused on amplification, parametric amplification, and so on. And of course, you can run a second order process to produce parametric amplification, but here we want to do a different process. And that is one in which you can see here, instead of Cauchys and cinches, we actually have just cosines and sines. And so this is a unitary process, much like a beam splitter, like a beam splitter transformation. And here, this theta nonlinear, at least for Chi-2, is just proportional to the square root of the power. So I can just adjust the power here, and I can adjust the cosine of theta to give me whatever I want. I can make this so this is 1 over square root of 2, or I can make it so that perhaps theta nonlinear is 9, pi over 2, in which case I can completely convert my idler to the signal. So the one that I'll be talking about today is the Chi-3 version. And again, it's very similar. The only difference is now we have two-pump wave, which of course brings an additional level of complexity, but also maybe an additional level of flexibility for doing frequency conversion. But everything is the same. I'm mediating between the blue and the green photons, or quantum states, whatever you have there. Now I have this pump and two pumps that are at these photons. But it turns out the equation, if you go through all the math, is exactly the same kind of unitary transformation. And so that brings some advantage. So, for us, Chi-3 is nice because all materials have Chi-3. I can do silicon nitride or almost even silica. The nice thing about it is you can really have a flexible range of wavelengths. So I can have it so that the frequencies here may differ anywhere from 10 gigahertz out to more than an octave, and everything in between, because it's determined by what these frequencies of these two pumps here. So that provides some flexibility that may not be so easy to do with a Chi-2 system. And lastly, you can have pretty broadband phase matching. So the system can operate over a broad range of wavelengths, perhaps. And then, if you're thinking of actually implementing this someday, and of course, a lot of people are interested perhaps in, for quantum computers that they need to switch frequencies. You'd like to do it ideally in a CMOS scale. So just to give intuition, because when you look at the picture here, it works out, but it's always sometimes good to have a physical picture of what's actually happening. And so if I look, we have this third order medium. And of course, I have three fields here. I cube them. I'm going to have lots of terms. And many of them, maybe competing, they're parasitic processes. But you can find one of the terms says that, for example, this idler field, I'm sorry, I have these backwards here. So this should be green, that should be blue. But the idea is that the idler field is roughly proportional to this kind of interference between the two pump waves, and then this field is just scattering over that interference here. So what's actually going on? Well, a chi-3 medium, you can think about it as a material that has an intensity-dependent refractive index. And so you can think that these two fields here, they actually interfere. You have regions where you have high and low index, and it's a grating. And because they're at different frequencies, the grating is actually moving. And this signal field scatters off that grating, and that gives you the idler. So in some sense, it's similar to like a crystal optic modulator or something. You actually have a grating, a moving grating, and just scattering off that grating. And if you do things right, what it looks like is that the power, let's say the signal and the idler, they obey this, if you look in terms of power, cosine squared, sine squared dependence. And so you see that the signal will actually decay as you increase nonlinear strength. This is going to be proportional to the product of these two powers, or the length of the medium, and then the idler grows in this way. And of course, the key part is this region right here in the center that people haven't paid that much attention to, which is this region where it really behaves like a 50-50 beam splitter. So, in our group, we worked on two chi-3 platforms. They're the two most probably boring chi-3 platforms you can think of: optical fiber and then silicon nitride. Okay, these are old materials. And, Marty and I had this conversation this morning a little bit about this. Is, why don't you use some of these more advanced materials and so on? And what are like the best chi-2 materials still today? Hopefully I'm not offending anyone. Lithium niobate, okay? An old material, but it's still, the one that has the highest performance. And then silicon nitride. These are really kind of old materials, but the thing that has been mastered in these materials is the processing and fabrication, which makes the losses very low. And of course, this has been true in optical fiber, which is, our whole world has benefited from this aspect, which again, it's probably the least nonlinear solid state material other than the fluorides that's available. But nevertheless, I can make 100 meters of it. And I'll say a key part about this because, and Marty and I had this conversation this morning, is there's a lot of great new materials that have far larger nonlinearities. So what's the key advantage here? Well, I have a fiber here where I want to do nonlinear optics, 100 meters long. And the amazing part about these materials is that if you can achieve phase matching, then all the molecules within that volume of that fiber, from the beginning to the end, are radiating precisely in phase throughout the entire volume. And that is a key aspect. Is, phase actually matters much more than intensity and everything else. And so it's that ability in these materials to have relatively large volumes with very low losses, which gives you a very big advantage. So I'm going to tell you, talk a little bit. So clearly the fiber brings low loss, except it brings quite a bit of Raman noise, which is problematic. Silicon nitride for me is like the perfect chi-3 material. I mean, okay, the nonlinearity could be larger, but it's 10 times already that of glass. Effectively, there's no Raman noise, despite claims. Every experiment we've ever done, we don't see any Raman noise in silicon nitride. Losses, we've been able to build on a chip 1 meter long fibers, effectively waveguides, where you're confining light to less than, roughly less than the wavelength. It's completely CMOS compatible. Even TSMC is now making silicon nitride. There's no 2-photon or free carrier absorption like silicon. And then, of course, the key part, which is a big advantage over fiber, is the ability to do dispersion engineering. This is something that we've worked on for a long time, and it's really allows you to do dispersion engineering from the visible out to the mid-infrared. And so we can work in any of those wavelength ranges by designing a cross-section of the fiber and doing some other tricks. So I'll tell you first about the work on optical fiber. So a key part, as I mentioned, is you have this 4-wave mixing process. and you have to do phase matching or dispersion matching. In this case, the dispersion matching is accomplished. So here I'm plotting the group velocity dispersion. And so what you always need roughly, and this is a rule of thumb, there's alternatives, there's other ways of doing it, but the rule of thumb is you need to put the signal idler on one side and the two pumps on the other side at the zero dispersion point, zero group velocity dispersion point. And then the frequency separation from the middle here to the middle there has to be equal. And that's it. If you do that, you can achieve phase matching. Of course, there's also a nonlinear contribution. I won't talk about that. If the pumps are equal, then you don't have to worry about it. So this is the noise sources in an optical fiber. And as I mentioned, there's lots of different parametric processes that can occur. So there's regular four-wave mixing, which leads to spontaneously scattered photons, which can produce a lot of noise. So here what you see, and again, I moved the figure here, so these are in the wrong place, but the pumps should be symmetrically about this peak here. And this is spontaneous pair production. So what we do is we put the pumps in the normal group velocity dispersion regime. That eliminates that you get this parametric gain or four-wave mixing photons that people use, for example, for pair generation. And then the signal idler you put in the anomalous group velocity dispersion side. They're very weak, so you don't have to worry about parametric gain here. And so then all that's left is really making sure that you've gotten rid of the Raman. And, I didn't understand this at the time, but, within my postdoc at the time explained this and showed this, and then it convinced me, is that if you look at Raman in glass at room temperature here, so this side is where you get a lot of the Stokes photons, and that's always produced. I said you're always going to have a lot of anti-Stokes photons, but it turns out that the number of anti-Stokes photons is very sensitive to temperature. And so by just cooling it, you don't have to go, to 1 degree Kelvin, but just even liquid nitrogen, which you can do, you basically eliminate all the noise photons through the Raman at 77 degrees there. So we have to put the fiber in a liquid door, total liquid nitrogen. But at that point, we get completely rid of all Raman. And so here's the setup. This was just an early experiment. We modified things, but it's still pretty close to this. So we have two pumps that are operating again in the telecom 1550 regime, and then our photons are around 1300 or so. And so this is what the noise looks like at room temperature. This would be in a window. Let's say if we create a window of detection, and this would be the Raman noise that you see here. And then even just getting down to 220, you can see, you're down to a very small number. And once you get to liquid nitrogen temperatures, you basically get no Raman noise. So again, this early work, we've done even better than this lately, but this just shows the rise of the signal beam. We give it a little pulse that's a few nanoseconds, about 5 nanoseconds or so. This is the idler decaying inside here. This is the classical. And actually with classical pulses where we can match the bandwidth perfectly, we can get to basically 99% conversion. But of course, it's harder with single photons. And in that case, we're a little bit less. This early experiments were around 93%, but we've gotten up to about 97% nowadays with single photons. But here you can see that the signal beam just decays here, just like you expect, like cosine squared. And then the key part, which is if you do a G2 measurement on the input, we have pretty nice noise photons at the input, but the converted photons also basically mirror that of the input. So that's indicating that we're preserving the quantum nature and there's not too much added noise. So here's more recent results. These were results from a great student, Chitali Yoshi, who demonstrated 97% conversion. She also looked at, as we try to increase the bandwidth, where can we operate? And of course, we're increasing the frequency separations of the pump here. And you can see it gets a little narrower, the bandwidth. If the separation is closer, the bandwidth is broader, but it still works pretty good. So here's the experiment we did. And so now we have this ability to do frequency conversion. It appears that you can, at least do complete conversion, but now we want to do this frequency beam splitter. So of course, the experiment that everyone asks you is how good are your photons? How good is your quantum system as you do a Hong-Ou-Mandel interference, which is a form of two-photon interference. And the way we do this is as follows. We actually generate correlated photon pairs that are generated at the modes of the silicon nitride microresonator. And so the pump you could think of is right in the middle here. And so pairs up, on opposite sides will be correlated. So these two will be correlated, these two will be correlated. The nice thing about that is they're generated fairly narrow band, of the order of tens of megahertz, because it's a microresonator, high Q microresonator, so they're fairly narrow in bandwidth. And they're also generated on a grid, which makes it very easy to match now the pumps, which we're using here to couple these two signal modelers. So what we do is we generate two correlated photons, and those are going to be our inputs for our Hong-Ou-Mandel interference. So, just to remind you this, I was actually a graduate student at the time when these experiments were done. Beautiful set of experiments done by a postdoc and graduate student in Len Mandel's group. And it's one of these things that, I understand it. I know I've gone through the math, but it's still kind of remarkable that it really works, which is, the idea that if I have two identical photons coming in and I look at the four possibilities, the photon can either be reflected, transmitted, can be transmitted, can be reflected, and it can be reflected and transmitted. And so you might think, okay, so 50% of the time I get 1 and 1 photons, but it turns out we don't. And that's because these two actually destructively interfere. You can think about it as these are fundamental properties of the beam splitter that conserve energy. And these two actually destructively interfere. So the only thing you get is 2 photons out this way or 2 photons out this way. So if I time the arrival of these 2 photons, and I call that a delay here, what I'll find is if I look at coincidence counts, I'll get 0 if everything is really good and well aligned, because I never get 1 and 1. So this is what is called the 2-photon interference. So now we have a system, but now think about it in frequency domain, where now I'm bringing in a green and a blue photon. So just like before, there's 4 possibilities. I can get both, this green photon is converted, so I have 2 blue photons. I can have neither of them converted, so I have a green photon and a blue photon. I can get the green is converted, the blue is converted, so then I also have a green and a blue photon. And then the last is I get the green doesn't get converted, the blue gets converted. And remarkably, if you go through all the math, it's not surprising. The math and everything is the same. Actually, those center ones destructively interfere. And remarkably, what you get is you can only get 2 blue photons or 2 green photons. And again, I know I've been through the math. It just seems amazing that this actually works out that way. That I'm only going to get, in this process of bringing in these 2 photons, just blue or green, and never get 1 of each. And so you have the same kind of Hong-Ou-Mandel interference that you did with the beam splitter. So, we did these experiments just to show a little bit of background. This is actually a paper, never got published. It was only in an archive paper. It has about 100 citations, but we just kept going to get rejected, and then Sven left, and we just never published it. But it's a really nice work because it shows these very narrow band photons. We had photons that were as narrow as tens of megahertz that came out of this. And I know people have done better since then, but at the time they were by far the narrowest band photons that have been generated to date. And so again, these are very high Q, so fairly narrow band. So this forms our source of these photons. And so I'll just jump to the conclusion here. But the red line is when we turn on the pumps and everything is perfectly matched. That is, the 2 pumps, their frequency separation matches the modes of the microresonator so that the correlated photons are generated and exactly matched up, in terms of blue and green to that host of the pump. And of course, if they're turned on and you look at the coincidence counts, basically the red line flat here is indicating you never get blue and red, or I'm sorry, blue and green. You only get blue or green, not both. And of course, we can at this point then start detuning the pumps away from that. And it's kind of interesting. You can go through the math here and you can see, so this is kind of like the coherence function for the microresonator, which is double exponential. And it turns out you get this function here as you start detuning the pumps away, and you can actually match it almost perfectly. And actually, it's entirely analogous to this kind of atomic system that was studied by Rempe's group. They actually had exactly the same expression and exactly almost the same data that we show here. So now we have the system. It seems to be behaving just like our beam splitter. We have this two-state system. And so we can now start thinking about that we have the block sphere, and we can start doing experiments like Ramsey interference with this system. So we can think about that, we have an atomic system here. They're separated by this delta E. We can send in a pi/2 pulse. We create a superposition. Then the system is allowed to go, undergo free induction decay. It evolves a little bit, requires a space factor between the ground and excited state. You then do another pi/2 pulse, and depending on how much you allow this to evolve, you can actually measure these Ramsey interference pulses. Okay, so this is it's been done and shown in a lot of systems. So our system, I'm going to operate through here. But we have the same kind of system, but it's all in the frequency domain. You start off with a blue photon. You apply your pi/2 pulse, which is this 50-50 beam splitter. You now allow this to just propagate in free space. It could be just an optical fiber. You apply another pi/2 pulse. And again, you should see the same kind of Ramsey interference, depending on how long you've allowed this to actually propagate. Lost my. So here was the case for a weak coherent state. Okay, this is working. Thanks. So here we can see for a coherent state, you get, it's straightforward, it's simple interference. But even in this case, again, we've gotten since then much better data, but we can also see this Ramsey interference even with single photons. So again, indicating that it's really behaving exactly like the same two-state system that we're familiar with. So I just want to make a comment here for a number of reasons. One is I could go on, but this is work that my student and postdoc for 1 year, Yun Zhao, who's working currently in Amir's group, did, which is really fantastic work, which is currently being written up. But having an optical fiber in a 77-degree Dewar is kind of not that convenient, especially if you're thinking about scaling it up. And so, one of the things my group and Yoon have been working on is to do this in an integrated photonic system. And, of course, a lot of groups are doing this now. You have very high quality thin film lithium niobate devices, and Marty and Amir are working very hard on this work. There's been work in bulk systems by David and Jonathan. And so this could be very attractive. Not only that, is the fiber, we're always kind of limited to the telecom band. And ideally, what we'd like to do is move into other wavelength regimes. And the dispersion engineering that you can get here can allow you to work in a much wider range. But of course, once you have a microresonator, nonlinearities are very strong. And it becomes much harder to put the pumps necessarily in regimes that are good. And so what you'd like to do is suppress all the other parametric processes that occur. All I've been showing here are just the ones that work, the ones that are going to work, and we've had to suppress through dispersion all the other ones. And here it becomes even more extreme in terms of having to suppress these processes. And Yoon came up with a very nice idea, which is, rather than using these gratings, for example, you could put a grating on the microresonator to enhance certain things. And that's what most people have done. But he said those tend to be pretty lossy. And so instead, what we're going to do is use the grating to suppress the undesirable frequencies. And in this case, there are multiple ones. And so he put a Moray grating, which is kind of two gratings with different spacings. And it turns out it really works very well. So here's, this was the state of the art, which is 25% conversion. At this point, Yoon here has now, in his most recent work, at least for, it's a little bit noisy, but you can get 93% conversion inside the microresonator, and actually for single photons, 50% conversion. We're not there yet. There are improvements that we can still make, but it certainly shows that eventually we can hopefully get this system operating comparable to what our optical fibers will.
Given that it's a linear system effectively, why does the efficiency go down?
Well, two things. One is there's a number of things. One is it's a lot easier with classical fields to match the bandwidths and everything of the microresonator and everything. When you're generating the single photons, you can't match them quite as well. There's also other noise processes that can occur that aren't even the nonlinear ones. There's fluorescence in the silicon nitride, which also makes it,
Okay, so you then optimize your pump intensities or something to reduce that.
Right.
Got it. Okay. Cool.
Okay, so, but the next step is now we have, I've only shown you for a simple case beam splitter, but the nice thing about this forward mixing process is ideally what you could do is just add more pump fields, and this is the scaling that we have, and now we can produce more couplings between all the quantum fields, and this can scale up. So this is was like our holy grail goal. We've done a lot of different experiments on this in both theoretical work. I just want to point out one thing. So you'd say, well, having all those pump waves, that's really hard. You have to put them all at single frequencies. But something my group works a lot on, which is optical frequency combs. And sometimes the combs, they say they're not really flat, but here's a device that we can make where we can actually produce combs, 75 lines, relatively flat, all over 0.5 milliwatt. Of course, you could amplify that more, but certainly we very efficient. The pump to the comb conversion efficiency is over 40%, and so this principle could then be amplified and serve as the pumps for some systems. So we can easily get to the number of wavelengths where we can scale this up much more than what you're seeing. You don't have to actually add lasers. So in the meantime, we did do this one experiment, which is to do the three-way version. And actually, while people have done this with wave, using what are called MMIs in integrated photonics, they're not so easy to design. But in our system, we can add an additional pump wave, and so we should be able to now split our single frequency photon here into 3 different colors. Okay, and so now, in principle, we can create a more complicated state, a QDIT state, based on that. And so this is now our 3-way beam splitter. I won't go through all the math here, but again, you can go through, you can actually solve this very generally for some arbitrary number of frequencies. And again, this is in the linear regime, but you can, work out all the math and all the phase match. And of course, everything gets a little more complicated, but it is pretty straightforward. And what it allows you to do is pretty much arbitrary coupling by changing the magnitude and the relative phase between these fields. And so it allows you, in some sense, to do, the 3-way interaction that people are looking for. So here's just a simple classical state that you get at the output. So let's imagine we have an input state where we put now not just 1, but 2 input fields, classical fields. You can go through all the math. And again, you can think about the phi's here as being just related to the pump fields, and the p's and q's are kind of like the cosine and sines. But you can go through all the system here and determine what the output state would look like for the classical fields. You can predict what the number of photons or the strength of the intensity of the fields at the output of the 3 fields might look like. And you can, we do the experiment. We now have 3 pump photons. We bring in photon pairs that we then bring in here. And so those are our 2 photons that we do. And then we do detection of all 3 ports coming out. So this is what it looks like. This is just a classical result in some sense. So there's just weak coherent states. So here we have the 2 input fields that are roughly at a photon level. And then we just bring in and see the growth of this 3rd field due to here. And you can see again, solid lines are just what those expressions show you. So again, the experiment shows very nice agreement. What's interesting is when you now go into the quantum domain, and again, as we know, just like Hong-Ou-Mandel gives you a very different result if you have classical coherent fields at the input and you put in quantum fields. And of course, the extreme of this would be kind of, boson sampling, where, the distribution you get after many layers is completely different from what it is here, what it would be for a classical state. And so here we can see for coherent state, if I look as a function of nonlinear strength here, we can see it just goes down and comes back up. It actually looks like cosine squared. But what you see is with the photon pairs, like the Hong-Ou-Mandel, you have a dip there that doesn't exist classically. We also get a dip for this state. So let's just stop at this point here. But this would be an indicator that you're in the quantum regime. In fact, you can show that this line here is precisely the line. It's a weird value in terms of the coincidence, but there hasn't been a lot of, there's been a lot of work on Hong-Mandel two photon interference, not so much when you have a three-way interference system, but this is kind of the behavior you get, and this line here represent the boundary between classical behavior and quantum behavior. Just like the G2 becomes less than 1. And so here again are experiments we did, and again I won't go through the details. There's some issues because of the phases of the pump field and preserving all those phases. But again, you see this dip that shows up here. It's not as large because of these phase fluctuations in the pump, but those are things that we could take care of in principle. But it's indicative that when you have two photon input here, you get into this non-classical regime as opposed to the simple classical kind of cosine squared behavior. So the last part I'll talk about, how much time? 5 minutes. But perfect. Okay. So so the last part I'll talk about is the idea of now we have this qubit here, and it's in the frequency domain, and is to actually try to use that to do quantum communications. So kind of the standard now is the two approaches that you hear a lot about, for example, is polarization. So you have vertical, horizontal, which represent your 0 and 1, and you can do quantum communication coded using, let's say, the BB84 protocol between Alice and Bob. There's the time bin version, which is you split your photon here, you apply a certain phase, and then you have a kind of a similar type of interferometer where you interfere them back here. And again, both of these allow you to do kind of block sphere type communication protocol. What I wanted to show are those that, although it looks great in practice, for example, if you look at polarization, and polarization is implemented everywhere, but it's not so easy. And here I just show one reason why. So this is a quantum network. It's called SkyQNet. I actually think it's the longest one in the US. It was really conceived at Stony Brook University in collaboration with Brookhaven National Labs, and it just in the last few weeks has reached Columbia. So we now, in the back of my lab, we actually have access to this quantum network here. It's dark fiber, no amplifiers. There's a company here called QNEC, which is developing quantum communication technology. But this is from this paper here, and this is the fidelity. So this is during the night, and you can see the fidelity when they're doing the quantum communication is pretty good. Then the trucks, garbage trucks, start showing up, and you can just see lots of just there. So this is what's happening to the polarization. Now, it's not to say they can't correct for it, but it's the fact that they have to actively, on a kind of millisecond time scale, correct for polarization fluctuations in the fiber during the day, and to get the quantum network to work. So this has to be done, and it's just they just accept it as part of the deal that you have this. So there is an issue with polarization, and so what we thought is perhaps we can use quantum frequency conversion to create now my frequency qubit here, which can be pretty robust to any fluctuations. Not only that, you could just send it on polarization preserving fiber, and then you don't have to worry about any polarization effects whatsoever. And it turns out that it's really hard to have a bit flip between let's say photons, even if they're like a few nanometers apart. It's not like they're going to travel down the fiber and all of a sudden this flips over. The intensities are very weak. You're not going to have any Raman or anything that might flip these two. And so it's a pretty robust way of doing quantum communications. And so again, I'll to finish up on time, I'll just say we put this in the lab. And again, this is just in the lab here, but we now have two quantum frequency converters, pretty good conversion efficiencies between them. We use this to generate our pi over 2 pulses, as I showed you earlier. And we communicate on different lengths of fiber up to 37 kilometers in this particular case here. And so, Alice could basically do the equivalent of rotating the polarizer. We can just have our frequency convert, do equivalent of, let's say, a pi over 2 pulse or so on, or different gates. So the early work was just to do Ramsey interference to see what is the quality of it. At 37 kilometers, it goes down to about 83%. There's reasons there that I don't think have to do with anything fundamental, things that we can improve in the setup, but it clearly shows that even over fairly long distances, we can do Ramsey interference over a pretty long distance. And this is just very recent results where we actually implemented the BB84 protocol. On this, again, this is over a 37-kilometer distance. And now we can do some interesting stuff, which is, okay, normally you need to detect 2 different photons, but what we can do is at the output, we just put dispersion compensating fiber to spread the red and blue photons and then detect. So now you only need a single detector. And so what you've done is you've said, well, the blue photon will come out here, the red one will come out here. And so I just need to time resolve that. So for example, Alice can prepare a state in 0 or a 1 state, and then Bob can take a look at those and do an analysis on that. Or he can prepare, for example, in this case, a Hadamard state, so we can convert a plus state to, let's say, a 0 state, or a minus state to a 1 state. And so it's indicating that you can actually use this. And it's fairly straightforward and simple and robust for the system. And of course, you can extend this easily to qubits, which is just adding more frequencies in our case, which again is pretty straightforward. So I'll just finish up. Sorry, Yoon, I didn't add you here. I did this last minute. But I'd like to thank a great group of postdocs and students, and Yoon, who did the work on the microresonator frequency converter. And in fact, the devices in silicon nitride were fabricated by Nicole's group, and again on some of the 3-way and the kind of the equivalent of the 3-photon interference we worked with in a Senhook Garcia's group. And again, we had a review article. This was actually one of Andy Weiner's last papers. Published a review article on frequency band quantum information that has some of the stuff that I talked about here, but not all of it. Thanks for your attention.
We have student questions.
Thanks for a great talk. I'm wondering, what is the polarization sensitivity of the conversion process itself?
It is polarization sensitive.
And do you guys do any sort of state
So for the case of fiber that we do in liquid nitrogen, it's stable over like a day, and so there you can we just have we just change the we do a polarization to convert it back to linear. That's it.
Sure.
Sorry.
So can you say a bit about the noise? For example, are the pump laser, those laser noise?
You're saying fluctuation? Yeah, it does matter. So those have to be good quality lasers, close to shot noise limited. I'd say as long as we're looking at the noise outside of the bandwidth, it should be okay.
Could you explain why photons with different frequency and consider is indistinguishable and do Hong-Ou-Mandel?
That's good.
Yeah.
That's a great question, because I forgot to emphasize that point. So when I learned Hong-Ou-Mandel interference, I was always taught, I think you'll even find papers, you have to have identical photons. But the key aspect is they have to be identical to the output. So the fact is that a different colored photon can actually be, let's say, a blue photon. You cannot tell if that came because of the frequency conversion process or because of blue photon just went through. So the indistinguishability that's important for that is actually the output, not necessarily the input. Of course, the input ones are completely indistinguishable. One's red, one's blue, or different color. And so the key part is you want the indistinguishability to be at the output of your beamsplitter. So I don't know if that answers your question.
Thank you.
Yeah, I was just wondering. So I guess
if you have different colors, so you have sort of this, you can't flip, but I guess you could still have dispersion and they could get offset or something during the travel. So I was just wondering, since you already have like kind of the ability to move them back and forth, could you like, make your two colors and then, using, I guess, dispersion or something, kind of shift them in time and then convert it back. So now they're the same frequency when they travel down the fiber and then
Absolutely, sure,
dispersion. And then I guess on the other side, then they don't need that. They could just use delays, right?
absolutely.
But then you're sensitive to high frequency patterns. So we could-
Yeah, I think it's about.
In this idea where you have like many different frequency encodings and you drive the gates with a frequency cone, how do you modulate each component to the right frequency?
So you're saying if you have a frequency cone, how would you modulate each frequency?
Yeah.
I mean, the separation there could be like 200 gigahertz. So it's enough where you could do the filtering and, you could use a ring resonator, for example. You could use a lithium niobate ring resonator, which would only modulate, it could be on the bus, but it only modulates that frequency. You can have it all on the same row, and each ring microresonator would modulate only that particular frequency. That's something that, I think could be done.
How much do I have to worry about the wave packets of the photons getting distorted?
I think if all you're doing is detecting, I think you're right that if you're worried about the interference, it could be an issue, but these are pretty narrow band photons. They're like 10 megahertz.
Doesn't that make them really long and thus more sensitive to that?
I don't know. I think dispersion and these other things, the dispersion goes like the bandwidth squared. So there's a huge reduction, I would say, in 10 megahertz, where you really don't have to worry about this.
How much of a limitation is the cross-phase modulation of the pumps on the single photons?
That's included in the process. So that's part of that phase matching that I showed you. If the pump powers are the same or roughly the same, the phase modulation actually vanishes.
So I guess this has somewhat of a limitation on your choice of pumps.
I'm sorry, say that last part again?
I suppose it sets some limitation on your choice of pumps, whether you use degenerate pumps or non-degenerate. If you want to cancel that.
I think there's ways around, you can, the dispersion can compensate a little bit for some cell phase modulation. So, there are things, if you're allowed to tune the system a little bit, you can get around that. But I will say that all that matters is, the simplest case of the phase matching is to make them the same. If they're a little bit different, which actually could be desirable in some cases, then that just means that you have to add some additional dispersion in your system that compensates for it.
I can ask a question. You showed that with multiple pumps, you have this more tunability on that beamsplitter, and I was wondering if you found good ways of efficiently wording the desired unitary
I think also you're asking, which is like, let's say, is there a way of determining, like, you want some kind of unitary transformation? What should the pumps do? Yeah, so there is that. I actually almost showed that slide where, Chitali did this analysis where she did for 12 pumps, did the analysis and show that you could pretty much get any arbitrary output. So you can, by changing the amplitude of the pumps and their relative phase, get to kind of the equivalent of like boson sampling type of behavior.
So when you're doing long distance communication with frequency beam,
You need to phase lock the local oscillator with the sender and the receiver?
Yeah, I didn't, that's an excellent question. I didn't, yeah, so here, let's see if I show, so here I show, so what you do is you have your two pumps that are coming in here. And then what you do is you attenuate them so that they can even send along the same fiber. They can be very weak. You send them along with your photons. And then you can then take those, amplify it, and then it gives you the phase lock. But you only have to do this locally, you know, so you just have to send them along and then take care of them. That's the next question. It's actually a two-part, which, you know, you figured it out immediately, but at the time we didn't appreciate it, and it took us so long.
So, more questions? Yeah.
But I don't think
Yeah.
so like so maybe like
Yeah.
I
don't know what's on.
yeah, also it's fine, like
Yeah.
Honestly, like, it's
yeah.
like,
One thirty people.
honestly, like, I've always got this.
Oh, yeah.
Yeah, I have.